So our final presentation today is by Dr. Hoda Azari, who is the FHWA's Non-Destructive Evaluation Research Program Manager. She's a structural engineer by education, and her expertise is in the area of non-destructive evaluation and structural health monitoring of transportation infrastructure. She has over 10 years of experience in these two areas of expertise. She's done extensive research studies for condition assessment and damage detection of transportation infrastructure and performed forensic investigation services to state DOTs. Dr. Azari is also the FHWA's technical point of contact for application of unmanned aerial systems, augmented reality, and artificial intelligence in highway infrastructure. Take it away.
Thank you. Thanks for the introduction. And I'm glad to be here today to share some of the findings of our ongoing research project, which is about use of UAS for bridge inspection. So this is the outline of our presentation. First, I'll talk briefly about traditional methods for bridge inspection, and then move into UAS application in bridge inspection, the payloads, the data that we get from UAS and sensors deployed on UAS, and at the end, what are the minimum requirements of sensors to repeat the regular bridge inspection. So traditionally, inspecting bridges requires some sort of work platform like ladder, snooper, or rope access, depending on type of the bridge and the traffic control needed and the ability to close the lanes. But regardless of the method used to carry out the work, the associated cost and time and danger is still a challenge. For example, snoopers requires training, expertise of the person. It's expensive. The rope access, it requires high level of expertise to be used safely. So UAS can be used as an access tool and as a supplement to hands-on visual inspection. It could provide a close detail necessary for a thorough and reliable inspection to do the bridge inspection safer and more cost-effective. So UAV themselves cannot do the inspection. They can be used as a supplement to bridge inspectors to assess condition of different bridge elements in accordance with the national bridge inspection standards. So UAV can provide a cost-effective way to obtain detailed information that may not be normally obtained through regular bridge inspection. So this picture shows the major component of UAS. You have the UAV, which is the platform. You have the sensors, which are deployed on the UAS or the UAV, and it's your data collection mechanism. You need at least two people, like the pilot who operates the UAV and the observer who spot the area for the pilot to capture data, the ground control station, and communication navigation link. So the UAS can reduce the cost of inspection in some cases, but mostly the data management associated with the data captured by UAS, it's a challenge. Advanced UAV platforms and sensors with experienced operator and experienced pilot might be required to get the maximum benefit. So based on a study conducted by Minnesota DOT, their average cost saving was up to 40%. And the cost saving comes mostly from the traffic control and eliminating or reducing the need for access tools. So generally, UAS works well for large bridges in open areas, and basically bridges that need some sort of access methods or traffic control, and it's basically good for areas that are difficult to reach. but it doesn't work well for bridges with high traffic, daily traffic, and in heavily wooded areas, and also fracture critical bridges, because the use of UAS for fracture critical bridges is limited with today's capability of sensors and cameras, because today's cameras is not able to see through dirt and debris and corrosion to find and see the critical defects. So with the current technology, the NBIS or National Bridge Inspection Standard require hands-on inspection on fracture critical members. So these are the typical sensors that are being deployed on UAS for bridge inspection, or on UAV for bridge inspection. One is GPS to locate UAV, ultrasonic sensors to that works like a collision avoidance on UAS, high definition camera for capturing HD images to measure or to record the surface defects or surface characterizations, infrared thermography cameras to acquire or capture infrared images to measure or record subsurface damages, and also LiDAR to get a 3D model of the structure, or to get a surface recording of the structure, like the surface defects. So for example, for the images that are captured by HD camera, defects can be identified and can be measured in a level of detail that is equivalent to a close-up of photo. As you see in this image, you can measure the gap. You can take a close look at the image and measure, take some measurements based on the photogrammetry's softwares and methods. Also, by using HD camera, UAS can get a camera into difficult to reach areas to help detect and capture images of structural defects during routine inspection. So UAS can be used as a cost-effective tool for obtaining information that just visual inspection or the bridge inspector cannot do without such a tool, not as effectively as UAS. Another example is IR images captured by IR camera deployed on UAV. So infrared images of bridge decks and elements are common techniques it works based on heat transfer and temperature variation. So basically the good areas and bad areas, for example, on a deck has a different heat radiation, heat transfer, so it can be detected through infrared camera. As you see in this picture, the blue dashed lines are delaminated area, and the delaminated area detected by sounding techniques, which is a traditional way of inspecting bridges. And as you see, there is a very good correlation between the sounding techniques and infrared camera. This is another example of using infrared camera and infrared images for a quick evaluation of the deck and also the superstructure, the truss members. Also, by using UAS, you can build a 3D model of the structure by capturing images and high-resolution images from different angles and different location of the structure. So it's a vast amount of data, and then these images are then processed by the software and create a point cloud generated from the photographs and the GPS data, and then by processing the data, we can build a 3D model of the bridge. This 3D model can be used for finite element model updating, which are used for like in monitoring field. We can use it for measuring deformation and displacement. We can use it for measuring section loss, volumetric changes, and also to monitor any visual changes over time. Also, as you can see on the picture in bottom left, you see that you can zoom in into your model and bring up just a detailed image from your model as if it's a high resolution image, and take a closer look, take measurements, or detect any defect, which would be hard by just the visual inspectors or bridge inspector to do it manually without use of UAS. This is another example that shows that you can get a detailed like image and visualization of a portion of the structure by zooming into the model and extracting that information as if it's just a picture. So that the 3D model can provide a high resolution like the image of the structure, of the bridge structure. Or the inspector can click on the model and bring all the photos that is related to that point. Again, to take measurements, to detect any defect, and to inspect the area. Again, another example, use of LiDAR to generate a point cloud of a bridge. And this 3D model, again, can be used for model updating, can be used to monitor any changes over time. So as part of this project, and it is still ongoing, we are setting some minimum requirements for cameras and sensors to repeat regular bridge inspection. And these parameters are the minimum sensor pixel, minimum ISO, minimum aperture setting, minimum shutter speed, the minimum standoff distance, wind speed, lighting, etc. So the first phase of the study was through field testings, and the second phase, which is still ongoing, is through a controlled environmental lab environment. So the first parameter was the ISO setting. During the field test, the research team found that the best imagery was captured by adjusting the ISO setting and setting the aperture and the shutter speed automatically by the camera. So the parameter that was changed in this case study was the ISO setting. So the ISO setting adjusts the sensitivity of the sensor to light. Increasing this setting allows more light into the sensor, compensating for the low light. So as you see in the picture, by increasing the ISO setting, we can get lighter picture, but also it appears more grainy, and it reduces the definition of the image. So based on this picture, you can see that if the lighting level is low, we have to adjust the ISO manually to a higher level, but not to a level that affect the definition and the resolution of the image. The other parameter that we looked into in field testing was type of lens. So the type of lens affects the quality of the image. If you use wide angle lenses, it increases the field of view, but it also distorts the picture. So if you want to take measurements from the picture taken by the camera, you cannot use the wide angle lenses, or you have to make some correction to the image before you use it for taking measurements. So as you see in these two images, the image on the right, we use wide angle lens. You see that the image is distorted. So like I say, if you want to use or the inspector wants to use this image to take measurements, they either have to correct it for the distortion or use not use wide angle lens. So like I said, the future work is investigating how to incorporate the data that we capture from a UAS into bridge management system. And the second ongoing work in this project is to do a parametric study in a control environment testing to set the minimum sensor pixel, ISO setting, aperture setting, shutter speed, and the minimum recommended standoff based on different variables, like if there is the collision avoidance on the UAV or not, if there is lighting, enough lighting or not, if there is any zoom capability on the camera or not. So that's all I have for today. If you have any questions, this is my email. We have the draft report ready, so if you're interested, I can share that with you. The control lab environment work is ongoing. If you are interested, I can keep you in the loop for future updates. Thank you.
Thank you, Hoda. Any questions? Yes.
For the ISO, have you looked into like higher ISOs? Like you said, give a lot more noise. Does that affect the, I guess the resolution, we'll say, of the final model that comes out?
We haven't tried it on developing a 3D model. We are just looking into see what parameters affect because basically the objective of the second portion of the study is to set minimum requirements for the sensors and see if the technology is at a point that can replace or can supplement more the visual inspection. So we are just looking at individual images, not the entire 3D model. Yes?
Do you have a standard sensor that you're using, or how you're defining parametric ISO performance across all sensors?
No, we are. It's just through all the sensors. We don't have any specific sensor type. In the project that we did, we looked into different sensors types. So we did a literature search about the available sensors, different manufacturers. But here in the second portion of the study, we are just looking into different parameters, not a specific brand or specific sensor.
Do you use a specific sensor in your test set?
Yes, it is documented, but
Is the final report gonna give a range of, like, it's not just gonna come out and say you must set it at ISO 400, because I'm guessing if you're under the bridge, you're gonna have different lighting conditions than you're outside. You just say the camera that you use has to have a range of 100 to whatever, 3200 or whatever. Is that what the focus of the report would be?
yes, so we are testing within the range of the camera, but also different environments, like under the bridge, when the lighting is lower than above the bridge, or maybe in different wind conditions. These are the more specific things that we're looking into the lab environment. We couldn't test everything in field. Yes.
So one other thing you had mentioned was the aperture. So like higher apertures, like f/22, something like that, you could run into diffraction, which would actually reduce the overall quality of the image as well. We've never mentioned anything like that.
We haven't looked at aperture yet. That's the only two, because the field is still ongoing. We haven't started the lab portion yet, but the field testing, we started with 3 bridges. 2 was the regular bridges, 1 was fracture critical bridges. So we haven't started looking at the aperture yet, but this is one of the parameters that we will be looking into. Yes?
Will the end result of this report be considered official guidance that we can bring to state agencies as something that says, hey, we can use drones for inspection based on these federal results? Or is this just more informational than official?
So I cannot comment on the policy side. We are on the research side. But once the research was requested by the Office of Policy, so that we can provide them with the information so that they can decide if they can include UAS in their guidelines. So until that process, it's just the report that you can share with the state DOTs that this is what Federal Highway Office of Research did, but it takes some time to get it into policy and guidelines.
All right, I think we'll conclude there. Thank you again, Hoda,
Thank you.
for your presentation.